Astronaut Pete Conrad joined America's space program in 1962. He piloted the Gemini 5 flight, setting a new record of 190 hours and 56 minutes in orbit. Conrad flew on Gemini 11, docking in outer space and reaching a record 850 miles above the Earth. Conrad then commanded Apollo 12 and walked on the moon for over 7 hours. He flew the first manned Skylab mission, performing spacewalks to repair Skylab's damaged surface.
Hi, I'm Pete Conrad. Before the Apollo mission, scientists could only speculate about the moon's composition and role in the history of our solar system. From the first steps on the lunar surface, we were able to tell volcanoes had been part of the moon's past, and astronauts carried many samples back to Earth for scientists across the world to study. The film you're about to see takes an in-depth look at our moon. From the 6 Apollo mission findings, we've revolutionized our theories of the Earth's age and origin. By studying the moon, we can learn the maturity process of planets. This will enable us to better prepare for the study of our planet. Plus, by getting to know the moon, we can prepare for the future usage and industrial development of this body rich in metals. The hours I spent on the moon made me realize the true potential of life beyond Earth. Watch with me as we learn about the planetary life cycle and discover what the moon is really made of as we get a new look at the old moon.
Each year since 1970, leading space scientists from throughout the world have gathered in Houston at NASA's Johnson Space Center and the Lunar and Planetary Institute to exchange ideas and information. The 1979 conference marks a special observance. It is the 10th anniversary of the first Apollo landing on the moon. In the space sciences, where it is common to deal with eons and millennia, 10 years is a mere blink of the eye. Yet in that brief span, those here today have witnessed almost total upheaval in their respective scientific fields. To say that we have undergone a revolution in lunar and planetary science is more than just rhetoric, when you consider how far we've come in a single decade. Before the Apollo era, scientists who wanted to learn more about the formation and evolution of the solar system didn't have much to work with. From the entire solar system, they had only 2 sources of materials available for direct analysis: meteorites that had fallen to Earth from outer space, and of course the rocks and soils of Earth. But the dynamic nature of the Earth has resulted in the processing and reprocessing of its rocks and soils for hundreds of millions of years, totally destroying its early geological record. As a result, an Earth rock more than 3 billion years old is a rare find even today. Most Earth materials are far younger. But meteorites that have fallen to Earth were found to be extremely old. The oldest, about 4.6 billion years, and most scientists believe that was near the time the solar system formed. So between the ages of Earth rocks and meteorites, there was at the time a gap of 1.5 billion years, a period totally erased from the Earth. Long before the Apollo era, the idea that perhaps knowing the moon would lead to a better understanding of Earth and the solar system had occurred to many investigators. And with the telescope, they studied its every surface feature. they charted the dominant light-shaded areas, the highlands, pitted and scarred from eons of meteoroid impacts, and the smooth, dark basins that Galileo, in the early 17th century, had called the Maria, or lunar seas. They were able to calculate the height of lunar mountains, some of which rise 5 kilometers above the terrain. They knew the length of ancient scarps or faults which may slice across the moon's face for 100 or more kilometers. From pole to pole, they studied craters, older ones with outlines barely visible, newer ones with streaks of displaced rubble radiating out from their centers, craters overlying craters, and craters within craters. Scientists thus came to know the moon's surface features in minute detail. Yet beyond what they saw, they could only speculate about its origin, its age, its chemical composition, its structure, and about what processes had shaped it in the past. There was no shortage of theories, but there were very few facts. By the late 1950s, improved technology in the form of automated spacecraft gave us a new perspective of the moon. These unmanned probes from both the Soviet Union and the United States sent back images never before seen by the telescope, including the first views of the moon's backside. From surveyor spacecraft that soft-landed on the surface, there were even some basic data on the nature and chemistry of lunar surface materials. Here, too, was the first concrete proof that landing craft and astronauts would not sink from sight in the powdery lunar dust. Yet for all the centuries of telescopic study, and more recently the flurry of automated moon probes, the detailed analysis of Earth materials and meteorites, in spite of all that was accomplished, prior to the Apollo program, we knew next to nothing about the history, composition, and structure of the moon. Extremely different views were held by eminent scientists the world over. Theories and opinions snowballed, and in the absence of facts, they clashed head-on. Unless we could obtain pieces of the moon for study and analysis, understanding it would remain an impossible dream.
5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Roger, we got a roll for
Tower clear.
Roger. Eagle, you're looking great. Coming up 9
On
minutes.
July 20th, 1969,
We're now in
the
approach
dream
phase. Everything
became
looking good.
reality.
60 seconds. Lights on. Forward. Forward. Good. 40 feet down, 2.5. Picking up some dust. 30 feet, 2.5 down. Straight shadow. 4 forward. 4 forward. Drifting to the right a little. 20. Down a half. 30 seconds. Forward. Just. Good. Okay. Contact light. Okay, engine stop. We copy you down, Eagle. Houston, Tranquility Base here. The Eagle has landed. Roger, Tranquility. We copy you on the ground.
After years of planning, the detailed on-site exploration of the moon had begun.
You're looking good here.
And briefly, the world stopped as people everywhere shared this greatest of moments.
Step off the limb now. Are you getting a TV picture now, Houston?
Even scientists who had spent years preparing for this day were awestruck by the sights and sounds from the moon.
Pretty good place. I'm gonna have to get on the other side of this rock.
Making the most of their brief time on the surface, the astronauts set up a small science station to return data back to Earth. It was the forerunner of other stations erected on later missions. It was this network that would allow scientists to keep track of the moon's geologic behavior for several years. Tranquility Base presented the Apollo 11 crew with an assortment of rocks and soils. Most of it appeared to be basaltic rock, the most common form of volcanic lava. Whether or not there had ever been volcanic eruptions on the moon had been one of the major pre-Apollo debates. Now, within minutes after the crew stepped onto the lunar surface, it was no longer an issue. But quick and easy answers would be the exception. Most discoveries about the moon would have to be built piece by piece from tiny fragments of information during the many months of painstaking work that lay ahead. When Apollo 11 returned to Earth, a carefully developed program of lunar samples investigation was set in motion. Geologists, physicists, chemists, biologists, several hundred scientists from here and abroad had pooled their talents for the task at hand. Although investigators worked with the same types of samples, they looked for different things. Some groups measured ages and chemical compositions. Others worked on the chemistry of minerals and their atomic structure, while some experimented, defining the properties of lunar rocks and soils. But not all of the investigators worked with samples. Some of them read electronic blips and tracings, the signals coming from the geophysical instruments of the Lunar Science Station. Here, a running account of the moon's internal activity, the basis for determining its structure, would be recorded and deciphered for the next several years. The techniques and procedures for investigating the moon were working, and working well. The goal now was continued exploration to obtain a variety of lunar materials from different geological terrain and to establish a network of scientific stations. Over the next 3.5 years, Apollo 11 was followed by 5 more lunar landings. All of the landing sites were near the lunar equator on the Earth-facing side.
17, Houston,
From first mission to last, the scientific gain grew steadily. A big factor was the lunar rover, used on the last 3 missions. With this new mobility, crewmen ranged further from home base, and along with modifications to the lunar module and the spacesuit, they were able to stay longer at the exploration site.
Okay, I copy that.
On the final mission, astronauts could extend their total exploration time to 75 hours. Quite a contrast to the 2.5 hours of Apollo 11. More and better measurements were also transmitted from the lunar science stations, which grew steadily in size and sophistication. Sample collecting, too, became more selective and better documented on the later missions. And for the first time, on Apollo 17, a geologist was a member of the crew.
Oh, hey, there is orange soil. Well, don't move it till I see it. It's all over. Orange.
On December 14th, 1972, the last Apollo crew lifted from the lunar surface, and with them, the exploratory phase of Apollo came to an end. But the scientific phase, which by then was well into its 3rd year, had already answered many of the major questions about the moon. The story that began to emerge told of a moon far more interesting and complex than ever anticipated. For one thing, moon rocks were found to be very old, falling in a range from about 3 billion to well over 4 billion years. Significantly, moon rock ages began about where the ages of the oldest preserved Earth rocks left off. So in learning about the moon's past, scientists were also filling in pieces of the missing history of the Earth. No new chemical elements were discovered, but there were minerals that scientists had not seen before. The moon was found to have no free oxygen, no water, and no trace of life, present or past. Seismic activity inside the moon was found to be extremely weak, only about 1/10,000,000th of the activity inside the Earth. Except for the impact of small meteoroids and the steady stream of atomic particles from the sun, the moon explored by the astronauts had been quiet and inactive for the last 3 billion years. But the investigation showed it was not always so calm. Rocks from the lunar highlands revealed an extremely violent beginning. Almost 4.5 billion years ago, shortly after the moon had formed, its entire outer shell was a seething ocean of molten rock, melting to a depth of from 100 to 300 kilometers. During the next 100 million years, it began to cool, and the outer shell began to solidify. Minerals began to crystallize. High-density minerals tended to sink. Low-density minerals floated to the top. When cooling and solidification were complete, these new distributions of minerals had formed the separate layers of crust, mantle, and core. This process caught a lot of scientists by surprise. Melting and separation into layers had never been proposed for the moon. What's left of the early lunar crust after being torn apart by meteoroids is the light-colored material we now call the highlands. But even as it formed, meteoroids were pounding it to bits. Scientists are not sure about the frequency or the intensity of cratering during the next billion years. However, they are certain that about 4 billion years ago, the devastation reached a peak. The clues were found in a class of samples called breccias, which are made up of fragments of different rocks, all broken and welded together by heat, some containing tiny spheres of glass. With breccias consistently showing age imprints centered around 4 billion years, the evidence was compelling. At that time, the lunar surface must have been bombarded and broken up on a massive scale. A population of extremely large bodies, some as much as 50 kilometers across, smashed into the moon. They blasted the crust apart and gouged out the giant Mare basins. The largest of the basins, Mare Imbrium, is big enough to accommodate most of Western Europe. The barrage on the moon was so intense that most likely the Earth received a simultaneous pounding. Probably the whole inner solar system was teeming with the leftovers of formation, the loose debris that had not been collected into planets. After this major cataclysm, the cratering rate began to subside, and the solar system rapidly became a fairly clean place. By now, the moon, the Earth, and the other planets had swept up most of the loose debris. The next stage of lunar history was recorded in the basaltic lavas recovered from the Mare basins. Some 100 million years after the heavy bombardment ended, heat from decay of radioactive elements began to build up inside the moon, eventually getting hot enough to melt the rocky material. In time, as the melting spread, the accumulated lavas were forced upward through faults and fissures to the surface, where they began to fill the large basins. Filling the basins, forming the lunar maria, much as they now appear, was not, however, the result of a single rampaging lava flow. Age dating showed that lava was extruded intermittently, in one place or another, for almost 1 billion years, from 3.9 to 3 billion years ago. After that, the moon settled down to a quieter existence, and has remained essentially the same to the present day. Among the subtle changes which have continued on the moon is solar wind bombardment, the steady flow of atomic particles streaming outward from the sun. Particles striking the moon many millions of years ago left their evidence embedded in lunar materials, and these can be detected today. This scanning electron microscope, for example, is studying the tracks left by solar particles as they pass through a lunar sample. By making such precise measurements, scientists are able to construct a long-term history of the sun's activity. The surprising result is that the sun has been a fairly well-behaved star for many millions of years. There were no noticeable sun deviations even during the ice ages of Earth, a finding that tends to weaken theories that link Earth's climate with luminosity of the sun. The samples did not completely satisfy a major pre-Apollo enigma: how the moon originated. Processing of the lunar materials by melting of the outer shell, meteoroid bombardment, and the long volcanic phase destroyed all traces of the moon's primitive starting material. However, investigators have recently discovered certain Earth-Moon chemical similarities that can be explained only if they originated in the same neighborhood. But the mechanism of origin could have happened any of three ways. The moon could have been torn from the primitive Earth and captured in its present orbit. The moon and Earth could have accreted from particles in the same vicinity at the same time. Or the moon could have condensed out of an early primitive atmosphere surrounding Earth. Lunar origin remains an open question that will not be easily solved. Before the Apollo program, scientists were struck by the differences in the Earth and moon. Many believed the moon was a solid homogeneous sphere, related more to primitive meteorites than it was to the planets. But after analyzing lunar materials, seeing the patterns of chemical elements, the minerals that had formed from these elements, and the arrangements of these minerals in rocks, they came to realize that the moon had all the earmarks of an evolved planet with a history all its own. The difference, they found, was in the separate paths of evolution the Earth and moon have taken, primarily the result of their different sizes and starting conditions. If the Earth and moon formed near each other, they probably started out with a similar mixture of elements, such as aluminum, silicon, and oxygen. Like the moon, the Earth probably experienced an early melting phase that resulted in its separation into layers. The heavy bombardment phase discovered on the moon must have been sustained equally by the Earth. But during the phase of internal melting and volcanism, their common ancestry began to diverge in a way that would set them apart forever. For one thing, the moon, being smaller, had a lesser share of radioactive elements than the Earth. And these are the elements that, in decaying, generate heat. Also, the heat that was produced was lost more rapidly, simply because the smaller the body, the faster it loses heat. The larger Earth, with a larger store of heat-making elements and the potential to hold heat longer, developed a massive molten iron core that would help keep our planet running, as it does now, for billions of years. The intense heat powers volcanoes, recycling rocky materials to continually produce new crust at the surface. Heat from radioactive decay also created a narrow zone of molten rock just below the crust. It acts as a sort of lubricant, allowing the crust to shift about as thin plates. It is these lateral plate movements that have given the Earth its wide variety of changing surface features. The moon, with a crust so thick and rigid, never experienced lateral plate movement. Its mountains, which tend to lie in rings on the periphery of the large basins, were built from materials displaced from the basins when they were formed by impact. Nor were lunar rills formed by crustal shifting or by the cutting action of water, as they often are on Earth. Scientists believe they are old lava tubes that have collapsed over the last 3 billion years. At the time the moon was losing heat, it was also losing its volcanic gases. And it is from such gases that atmospheres form. But with a weak gravitational field, again the result of size, the moon was unable to retain even the heaviest gases. Earth's gravity held most of its gases, gases that eventually formed a primitive atmosphere. And from that atmosphere came torrents of rain for millions of years. The basins were filled, and the Earth had oceans and seas, lakes and rivers. And from the water, life itself would eventually arise. The moon, with no chance of forming an atmosphere, could not develop even the lowest forms of life. It was just too small to make it. After about 1.5 billion years, it reached the terminal phase of its relatively short evolution. The story of the moon is still not complete. Although its historical outline, once it formed, has been firmly established, its basic structure and chemistry have been determined, many questions remain. Only about 10% of the samples returned by Apollo astronauts have been investigated in detail thus far, so a lot of work lies ahead. Deciphering the complex breccias and core samples is slow and tedious work, but it is here that extremely complicated measurements are now being made. Measurements aimed at uncovering facts about the moon's origin, its first 100 million years, its volcanic history, and more about the history of the sun. When will we return to the moon? No one can say for sure, but certainly it has a role to play in the future. For a science colony, its location, the lack of a distorting atmosphere, make it a natural choice. As a staging base, the moon may someday launch exploratory missions to the planets and beyond. The moon is also a potential mining site for extraction of its abundant storehouse of metals, aluminum, titanium, calcium, iron, raw materials that could be used for building large-scale structures in space. Today, after 10 years of lunar and planetary investigations, interest and momentum continue to grow. The lessons learned from the moon are being applied to the Earth and to the other planets, especially nearby Venus, Mercury, and Mars. The processes observed on these planets are as strange as ever, but no longer are they mysterious. Scientists see them as extensions of patterns which are now familiar. And in time, they will understand their structure, their evolution, how they relate to Earth, and eventually, how this solar system of ours came to be. Apollo was much more than a triumph of technology. Like Columbus' voyage to the New World, the Wright brothers' flights at Kitty Hawk, the Apollo missions to the moon mark a major turning point in human history. Apollo was the first step in a journey that will never end.
Move in.
4 rooms Earth view. Sounds far-fetched at the moment, doesn't it? But you know, we may be seeing ads like this in the not-too-distant future. In fact, there's the equivalent of a small bungalow out there in space right now that's empty and available, with a beautiful view of Earth. Skylab, a bungalow that has already had 9 tenants. The main purpose of Skylab was to make space flight more useful for man's endeavors on Earth. As NASA Administrator James C. Fletcher put it, Skylab marked the transition from exploration to the exploitation of space. As has been said, the average taxpayer is entitled to ask, what's in space for me? Well, the results from Skylab will, we hope, answer that. Let's take a look now at the development of the Skylab space station itself. As I said before, this was really an economical venture to which the earlier major space programs contributed greatly, enabling the Skylab project to use flight hardware already in existence. It's 48 feet tall and 22 feet across, with a 13,000 cubic foot interior. 10,000 cubic feet of working space in the main section alone, the equivalent of a small family bungalow. Skylab is divided into a lower floor with crew quarters, wardroom, and medical experiment area, with an upper floor for space technology equipment. The multiple docking adapter provides docking ports for the command module, as well as housing the control console for the solar telescopes, and a series of cameras for conducting Earth resources observations. The command module, used to take the astronauts to and from Skylab, is identical with that used on the Apollo flights, and left over when that program was cut back. So, as we can see, much of the hardware needed for the Skylab program was already available. The unmanned orbital workshop was launched in May of 1973 atop a Saturn V rocket from Pad A, right here at Kennedy Space Center in Florida.
10, 9, we have ignition sequence start. The engine's now building up to 7.7 million pounds of thrust. We have a launch commit and we have a liftoff. The swing arms moving back.
When the flight was scarcely a minute old, a serious problem developed with the workshop. Mounting temperatures in the workshop indicated the failure of the meteoroid shield, which was actually torn off by the slipstream during launch. An hour after launch, the ground controllers in Houston were still waiting for confirmation that the workshop's solar array panels had deployed, a signal they never received. Of course, the launch of the first Skylab crew scheduled for the next day had to be postponed until solutions were found. The urgent need was to stop the rapid temperature rise, which was immediately accomplished by ground control in reorienting the workshop so it was no longer broadside to the sun. The next 10 days were hectic. Immediately, teams were formed to provide answers to the problems. A major objective was to design and fabricate a thermal shield that could be deployed on the workshop to make Skylab habitable. Throughout the United States, teams worked round the clock in an all-out effort to perfect such a design. Meanwhile, here at Marshall Space Center in Huntsville, Alabama, crews were evaluating installation of a parasol device in the Skylab underwater simulator. In conditions approximating zero-G, they also trained underwater in methods of freeing the jammed solar panel. But the actual work would have to wait on an eyewitness assessment by the astronauts in space. Time was becoming critical if Skylab was to be saved. Relief would come only from the thermal shield parasol, which would be deployed by the astronauts when they arrived at Skylab. During the early morning hours of May 25th, almost 10 days after the original schedule, a Saturn 1B was ready to launch an Apollo spacecraft for the first manned visit to the Skylab orbital workshop, with astronauts Conrad, Kerwin, and Weitz aboard.
We have launch commit and
Skylab 1 was on its way, the first step in the fulfillment of an opportunity to use men in space for practical humanistic benefits. By mid-afternoon, the crew rendezvoused with Skylab and performed a televised fly-around to assess the damage. Most of the predictions were confirmed. The meteoroid shield had been ripped away, exposing the workshop's skin to the sun. One of the solar array panels had been completely torn off, and the other, only partially deployed, was held in check by an aluminum strap, a fragment of the meteoroid shield. As astronaut Conrad put it,
Expected solar wing 1 and 2, right, is gone.
an unsuccessful attempt was made by Weitz at freeing the panel, working in the open hatch of the command module before docking with the workshop. After a night's sleep aboard the command module, they entered the workshop and took steps to deploy the parasol. In mission control, optimism that the mission would be saved wasn't long in coming, as external skin temperatures began dropping rapidly, and within the workshop, too, they had started to fall. The parasol was doing its job, but there was still a shortage of electrical power. The stuck solar wing would have to be pulled out fully. Thanks to the work of the backup crew at Marshall, where procedures were worked out for freeing the solar panel.
It's all the attention I can take.
Astronauts Conrad and Kerwin went on their first spacewalk to repair the damage. This took 3.5 hours, and it was difficult work. But man prevailed, and they were able to sever the strap and pull out the panel.
Let go, let go, let go. All right, it's got it.
Within hours, the power situation was nearly normal. The mission could continue. A mission transformed from near ruin to success. From the beginning of manned space flights, there's been a concern about the ability of man to survive flight through space and be able to perform satisfactorily in prolonged periods of weightlessness. This was a major concern and objective of all 3 Skylab missions, and was especially true on this mission. For the first time in space, there was a medical doctor aboard to supervise the tests in the Life Sciences program, astronaut Dr. Joseph Kerwin. This lower body negative pressure test provided valuable information on the cardiovascular system, carefully checked and monitored on the control panel, which supported all medical experiments. A measure of motor sensory performance, an experiment designed by a high school student, using a punchboard apparatus for eye-hand coordination to measure changes in motor sensory skill of the crews. Balance, orientation, and perception, so important to man's ability to function efficiently in space, was another of the life science tests. The astronauts were instructed to exercise frequently, and one of the techniques was the ergometer, or bike, to help keep them in shape. This also served as a test for possible changes in metabolic activity while working and living in a zero-G environment, as well as a check on heart rate and blood pressure under these workloads. Throughout each mission, a vast number of tests were made on eyes, ears, nose, throat, and blood samples were taken and returned for post-flight testing. Actually, we've seen only a small portion of the medical tests covering muscle and bone development, heart and blood tests, perception and equilibrium, and even cell growth. The ability to monitor, record, and transmit medical information over such a distance on the most advanced equipment yet devised will prove invaluable and undoubtedly be adapted for use in hospitals here on Earth. The tenets of Skylab certainly indicated that men could live comfortably in space for long periods of time with no apparent harm. It can be said that with Skylab, we have completed the most extensive medical space missions ever flown and learned many new things about man in weightlessness. Outer space is a truly revolutionary platform for materials processing, since all of the adverse effects of gravity are absent. This makes it possible to perform operations in materials processing and manufacturing that would be virtually impossible here on Earth. Many space processing experiments were performed aboard Skylab in a vacuum chamber and heat treating apparatus, including an electron beam gun and small electric furnace. The formation of crystals might well be the most valuable of all the manufacturing experiments. This resulted in crystals 10 times larger than those grown on Earth, with a much better uniformity of composition, so important in the modern field of electronics. This will result in systems that will perform more functions, will be faster, will require less power, will be smaller and less expensive to manufacture. The pocket computer, so widely used and popular today, is a direct result of space technology. As Professor Harry Gattos of MIT says, it is no longer a matter of speculation that materials processing in space presents one of the greatest opportunities ever afforded to benefit mankind. And kids, when it comes to blowing bubbles, how about this? You can puncture them, pull them, and pick them up, but they still won't break. As you can easily see, getting from place to place is no problem in Skylab. Weightlessness can be lots of fun, too, as Pete Conrad shows as he exercises, much like a squirrel in a cage. No circus acrobat or Olympic swimmer can match this. We all know Alan Shepard was the first to play golf on the moon. Well, here's the first space ball game ever played. The first 3 tenants of Skylab returned to Earth after 28 days in space. When trouble developed at the start of this mission, we might have despaired and written off Skylab as so much space junk. However, that was unthinkable. What the ground teams and astronauts did in saving the project, moreover, proved the crucial value of man in space. Future missions were assured. Early one morning, late in July, a month after the return of the first crew, Skylab 2, the second manned mission, was launched, with astronauts Bean, Lausma, and Garriott aboard.
And the second manned crew has cleared the tower.
During the 8-hour chase of Skylab, one of the 4 thrusters used for maneuvering their command module sprung a leak. Mission Control ordered the astronauts to shut the leaking assembly down. Bean still managed to dock perfectly. Six days later, another thruster sprang a leak and had to be shut down. The thrusters are needed to orient the capsule so that its main rocket can fire in the right direction for safe re-entry and return to Earth. For the first time in the manned space program, NASA had developed the ability to perform a rescue in space from a disabled vehicle. Round-the-clock preparations were immediately begun to activate the Skylab rescue vehicle, the rocket assembled and an Apollo craft modified. The Saturn 1B rocket was rolled out to the pad, ready to launch the rescue ship into orbit. Meanwhile, the 2 leaks were found to be unrelated and not as feared indicative of a general system breakdown. Computer studies and ground simulations showed that the capsule could be steered with half its operating thrusters, and the astronauts were told they could stay aloft for the 59 days as planned and continue their scientific studies and experiments. The most important package of scientific instruments on Skylab was the 12-ton telescope mount with its 8 solar telescopes to permit a study of the sun. The importance of these studies and benefits cannot be exaggerated, especially when we consider the natural resources and energy crunch that is upon us today. The possibility of this research teaching us how to better harness this energy to power our cities and homes with an inexhaustible supply of clean, non-polluting power becomes a major goal. When people think of astronauts, they usually visualize them as high-ranking military officers and daring test pilots, forgetting that some are also scientists with advanced degrees in physics, electrical and aeronautical engineering, and medicine. The value of men in space as true scientific partners in space science research is most evident in the Solar Studies program, because that allowed photographic film to be used, resulting in spectacular photographs being returned to Earth. Pictures such as this can only be made from space above the Earth's atmosphere with a special instrument, a spectroheliograph. Notice the comparison of the size of Earth with the large eruption of the sun's atmosphere. Other wavelengths were used to help follow changes in the sun apparent when this photograph was analyzed. Such X-ray photos permitted further coronal study, unveiling faces of the sun never before seen by Earth-bound observers, giving radically new knowledge of the sun and ways it may affect the Earth. Solar studies and stellar astronomy were features of all three Skylab missions, and this solar flare, photographed on the third mission, was the most spectacular ever recorded, radiating more energy than has been used by man since the beginning of civilization. The sun has no energy crisis. It puts out the entire annual world energy demand thousands of times each second. This gives added meaning to the words of Wernher von Braun when he said, "We hope one of these days to harness this energy on Earth." High priority was also placed on a machine that would allow an astronaut to move freely about outside a spacecraft. Using the Skylab's upper dome area to explore this kind of flying characteristic, the astronaut uses a maneuvering unit which could shuttle him between spaceship and satellite. This will prove to be invaluable in space flights of the future. There were also 19 experiments carried out specifically for high school students. One brought other passengers aboard Skylab 2, the Spiders, Anita and Arabella. This was an experiment to find out the structure of the web they would spin in the weightless state. They soon adapted to space and spun a web quite easily. There was a problem, though. When they ran out of food for the Spiders, they shared bits of filet mignon with them. Oh, for the life of a spider in space. The Skylab 2 crew spent almost 14 hours in spacewalks, augmenting the parasol with a twin-pole sunshade, changing film for the solar telescope, and retrieving canisters containing over 77,000 pictures of the sun from outside the workshop. After 2 months and some 24 million miles, the scientific journey of Skylab 2 ended, bringing back scientific data and secrets of the sun that had been kept secret for billions of years by the dense blanketing of Earth's atmosphere. In November, after a 6-day delay to replace cracked stabilizing fins, the third mission soared aloft, with astronauts' cars Gibson and Pogue.
Lift off, the engine's building up to 1.6.
Skylab 3, the longest of the manned space missions. One of the major projects on all three Skylab missions was the Earth Resources Experimental Program, which will certainly show the man in the street that space can be of everyday use in solving some of the world's most pressing problems, such as pollution, locating resources, and feeding the hungry. Special cameras were designed for this work. This program again brings out the importance of having men in space. For the astronauts were trained to observe specific places on Earth. They brought back photographs such as these, taken in the visible and near-infrared wavelengths, resulting in countless discoveries about the Earth in many different fields, in the inventory of water resources and study of pollution, seen so clearly in this photo of Lake Michigan in the Chicago area, in regional planning and development. Here we see the densely populated area of Baltimore and Washington, D.C. Information obtained will result in better warnings given of impending storms, such as the astronauts observed from space in the Caribbean and Pacific. This photograph of Hurricane Ellen in the North Atlantic revealed that the walls of the eye of a hurricane were sloping, which caused energy to be fed into it, a fact heretofore unknown and of utmost interest to meteorologists. In agriculture, for crop census and yield, soil moisture, and crop infestation. For example, in photographs of the desert areas of Africa, discoveries were made of the extent of damage caused by drought and incorrect cultivation methods. Valuable discoveries were also made in the field of geology to help locate natural resources, minerals and oil, so important to the world today in the light of critical shortages. Faults and changes in plate motions of the Earth, never before seen by man, were observed and studied, as were forests and range. Oceanography, the study of current flows and eddies, such as the Falkland Current, never before photographed. Aids to ship navigation, to lessen the possibility of damage to cargo and ships, and reduce the chance of major oil spills. Mapping, especially in such areas as this in South America, never before done accurately. This perspective from an orbiting spacecraft, such as Skylab, gives us a better way to inventory and monitor our resources, and provides us with information at a cost we can afford. While it will take years to study and analyze the thousands of pictures taken from Skylab, we cannot overestimate their actual value in improving our life here on Earth. Meanwhile, let's go back to the comfortable environment of life in space. And speaking of comforts, the comforts of home were not neglected either, as the astronauts could enjoy weekly showers, and if they could find a foothold, wash and shave, and even prepare their own food to individual taste. No more just eating out of a tube, as on earlier space flights. Crewmen enjoyed space luxuries never before available. Even man's sleep was monitored by a cap with sensors, as each astronaut bedded down vertically in a sort of sleeping bag in his individual sleep compartment, or should I say, stateroom. It was found, by the way, that the quality of sleep compared favorably to the astronauts' normal sleep pattern on Earth. Determining weight in a weightless world is a real problem. With no gravity, there is no weight, and normal scales cannot be used. Since many of the biomedical experiments require measurement, this odd-looking chair was devised and used to keep a careful check on the weight of the astronauts. Small masses were also measured on a device so sensitive it could determine the weight of a postage stamp. The next time you do your push-ups, try this. It was quite a chore when the astronauts got ready to go outside for a spacewalk. Fast-action photography, however, makes it look easy. It is much like suiting up Junior to go play in the snow. The Skylab crew spent 21 and a half hours outside the workshop in spacewalks, changing and retrieving film, observation, and repairing equipment. As on all three missions, Earth observations continued. While Skylab centered most of its work on practical uses of space, its crew didn't neglect precious opportunities to enrich science's knowledge. Cameras zeroed in on promising targets of opportunity, of which the most noteworthy was the comet Kohoutek. While its observations from Earth were not as spectacular as hoped for, Skylab's solar telescopes plus 2 spacewalks with portable cameras gained amazing results. Actually, the Skylab instruments were the only means available to scientists anywhere to observe the comet during its close passage to the sun, as this stop-motion film shows. The fact that the astronauts were able to observe the comet at this time and even make sketches proved scientifically valuable in collecting basic data needed to make the greatest advance in cometary research since Halley's time. While we were celebrating the holiday season of 1973, each in his own way, there was a special celebration aboard Skylab 3. The Skylab Christmas in Space. And of course, that included the stockings, hung by a very unusual Christmas tree, painstakingly constructed out of food cans and decorated by the astronauts with a very special star on top, Comet Kohoutek. And now, a Christmas message from space, showing concern for people everywhere.
From the Skylab 3 crew, we wish to extend to people around the world the message of peace, goodwill, and human understanding.
After setting a new record of 84 days in space, the third manned Skylab mission ended with a splashdown and recovery in early February of 1974. It's impossible to single out one thing as the most important among the more than 2,400 experiments performed during the Skylab missions on a flight path that covered almost 75% of the Earth's surface. It is certain, however, that Skylab has established a basis of factual data for the design of future space systems and the planning of future manned operations in space. Even more important, it has demonstrated that man has important work to do in space. And for humanity in general, there is no doubt that this use of space makes an important contribution in allowing man to manage his affairs here on Earth more in harmony with nature. Before the crew left the space bungalow, they configured it for a possible revisit by somebody, perhaps by the future space shuttle, or as the space administrator said, a little green men from space. The orbital workshop will continue in a 270-mile-high orbit for 10 years or more. It's up there right now. Maybe you'd like to be the next tenant. 4 rooms, beautiful Earth view.
Walter Cunningham joined NASA in 1963 after doctorate physics work at UCLA. He flew on Apollo 7, a mission exercising the docking and maneuvering of the 3rd generation of spacecraft, plus the first mission to televise onboard crew activities. He has logged over 4,500 hours of flight time, and his last assignment was as chief of the Skylab branch of the Flight Crew Directorate.
Hi, I'm Walter Cunningham from Apollo 7. When you think of our world, you probably imagine thousands of things. Different places, different faces, millions of people and animals and plants. The world in which we live is amazingly vast and diverse. But what about the universe? The film you're about to see is narrated by Orson Welles. He brings to your attention what many of the world's most distinguished scientists conclude. Life is out there. Maybe not the giant Martians from Orson's famous 1938 broadcast, The War of the Worlds. But beyond science fiction, to the scientific facts of amino acids and other elements of life that are found outside of the Earth's atmosphere. It's an exciting revelation that there may be intelligent life in outer space. Are any of the stories and sightings of UFOs and aliens true? Do our minds compare to theirs like the animals compare to ours? Will we reach them before they reach us? Watch with me as we try and determine who's out there.
Before the cylinder fell, there was a general persuasion that through all the deep of space, no life existed beyond the petty surface of our own minute sphere. We know now that in the early years of the 20th century, this world was being watched closely by intelligences greater than man's. Across an immense ethereal gulf, minds that are to our minds as our minds are to the beasts in the jungle. Intellects, vast, cool, and unsympathetic, regarded this earth with envious eyes, and surely drew their plans against us. Hello, I'm Orson Welles, and I've been quoting from another Welles, no relation, H.G. Wells, the distinguished novelist, historian, prophet, who was also the great master of science fiction. He wrote The War of the Worlds, on which was based a certain notorious radio broadcast, which, as some of you may remember, sent many thousands of our listeners panicking into the streets all over the country. H.G. denounced me for doing it, but later when he realized that our broadcast, like his story, was not intended to cause riots, but just to entertain, we got to be good friends, and I was forgiven. Whether all those people who jammed the highways and even took to the hills to escape the Martians have forgiven me is another matter.
This is it. We thought that this was it. Listening to that show, I said we were very impressionable at that age because of Buck Rogers and Flash Gordon, and that really made a big impression on us.
One fellow in particular who owned a store took the money from his cash register and loaded his car up with food and took off for the mountains and left his wife and children at home.
New York City was just demolished, and they were coming closer.
All of North Jersey is an inferno, and they are proceeding south.
I can conceive of no nightmare as terrifying as establishing such communication with the so-called superior, or if you wish, advanced technology in outer space.
George Wald is a Nobel Prize-winning biologist, one of a group of distinguished scientists meeting on the subject of extraterrestrial life. All of the people you will be seeing in this program, scientists, radio listeners, Orson Welles, have one thing in common. Each has had reason to believe in the likely existence of non-earthly life in the universe.
I think there's no question but that we live in an inhabited universe that has life all over it.
What I'm imagining is the facts that I've just stated becoming generally known, so that people know that out there is a million other civilizations. They all look fabulously ugly, and they're all a lot smarter than us. That seems to me useful and a character-building experience for mankind.
From the monstrous Mars life of his famous broadcast, Orson Welles will be taking us through science fiction to science fact, to the new view of extraterrestrial life now emerging from probes to the planets, interstellar discoveries, and findings about the nature of life itself. A real picture as astonishing in its way as the science fiction of 1938.
If there is life out there, intelligent life, how did we ever get the notion that it might be otherwise than friendly? Well, Mars, of course, is the god of war, so the planet bearing his name might be expected to have warlike intentions. In our broadcast, the Martians were as aggressive and ruthless as any human being. Ridiculous assumption on the face of it. They were supposedly as bad as we are, at our worst, and also much uglier. They brandished death rays in their slimy tentacles. And for a while at least, just toward the end of the radio play, they appeared to be totally invincible. What finally stopped them? Well, here's the way it went. In the words of the mythical Professor Pearson of Princeton, who was our commentator, I remember, he said, writing in his journal when the whole thing was put together again and the world was in business, I remember wandering through Manhattan, standing alone on Times Square, catching sight of a lean dog running down 7th Avenue with a piece of dark brown meat in its jaws. I walked up Broadway, past silent shop windows, and suddenly I caught sight of a Martian machine. And then across Columbus Circle, I could see, standing in a silent row, 19 of those great metal titans, their cowls empty, their steel arms hanging listlessly by their sides. And I looked for the monsters that inhabit those machines, and then, before my eyes, I saw them stark and silent, the Martians themselves, with a flock of hungry birds pecking and tearing brown shreds of flesh from their dead bodies. And later, when their bodies were examined in laboratories, it was found that they had been killed by disease bacteria, against which their systems were unprepared. Slain after all man's defenses had failed by the humblest thing that God in his wisdom had put upon this earth, the common cold. And that's the way it was. Well, quite a lot of things have happened in the world since then. An invasion from the planet Mars, that at least is one thing that didn't happen. But in a way, you know, we have been invading Mars. If Mars hasn't exactly been invaded, well, it's certainly been investigated, not attacked, but thoroughly, very thoroughly studied. Observations of Mars had begun long before our broadcast, and even back then, in 1938, it seemed plausible to many people that life could have developed on Mars, just as it had on Earth. Peering through telescopes, scientists had seen what? Well, first a planet that, like our own Earth, had polar ice caps. They were fascinated to see that the ice caps grew and receded with each year. Large areas changed color with the seasons. Did that mean vegetation? Straight lines were sighted on the planet's surface. Some called them canals. The American astronomer Percival Lowell believed that these Martian canals had been created by an advanced technological civilization. First in 1965 and then again in 1969, NASA sent spacecraft to fly by Mars and send back scientific measurements and close-up photographs.
This is picture 21, a red picture, wide-angle picture, fantastic picture. That's beautiful. That's beautiful. Look at those little craters. This is a narrow-angle camera view.
The Mariner missions were great achievements for the scientists. But the pictures of Mars showed a world of total desolation, Was Mars less like the Earth then and more like the Moon? There were no canals, no cities, no areas of cultivation, no signs of upheaval or layering in the Martian crust to indicate that the planet was active or evolving geologically. The pictures revealed no volcanoes to spew out gases that could enrich the atmosphere. And water, so essential to life, seemed to be present only in traces. The atmosphere was so thin as to make the possibility of life seem even more remote. For the fans of science fiction, not very exciting. But for scientists, the whole excitement is finding out the facts. That's the whole name of the game. Now, these first flybys had revealed only some of the facts. But all the same, the exploration of Mars and of all the other planets of the solar system was actually getting underway.
I can't feel that any person with any soul can look out on that universe that surrounds us and can imagine the immensity of it and the history of it without being rather impressed with the idea that we, as little atoms made of the same stuff those stars are made of, have the capability to regard the other part of the universe. One piece of the universe has the ability to look at another part of the universe and wonder about it. That's a very amazing thing, and it brings into one's mind all kinds of thoughts about religion and philosophy and so on. But don't ask me about life on Mars, okay?
In the fictional Martian story, in the War of the Worlds, it was understood that the Martians were fighting for their own survival. Their planet was growing so cold and inhospitable that they might perish if they remained. While real life confined to such a planet would fight for survival by trying to change itself, by evolving. Every living thing on Earth has evolved from the lowly, the invisibly small microbe. Given nourishment, the microbe will grow colonies so vast that they rapidly become visible to the eye. Here on our planet, microbes have adapted to survive the most hostile conditions. Arid deserts, the frozen Himalayas, in trenches under thousands of tons of pressure in the ocean deeps. Biologists at Ames Laboratory are discovering adaptive capabilities in life forms that a few years ago would have been regarded as fantastic. Within the cooling systems of atomic reactors, organisms have been discovered flourishing, where radiation could be expected to destroy any living thing. In hospitals that use ultraviolet for sterilization, strains have been found resistant to the killing radiation. Biologists are growing organisms in salt solutions, in acids, in alkalines, in ammonia gas, in boiling hot springs, in ice that is thawed for part of every day. In the vacuum of a space simulator, life forms have been flourishing for years without oxygen. Scientists are studying the kinds of environments that could challenge life forms on the planets and moons of the solar system. In 1971, Mariner 9 arrived at Mars, equipped to go into orbit and stay for a while. A good thing, too, because when it arrived, Mars' surface was obscured by a global dust storm. As the storm abated, a whole new Mars began to make its appearance. The first feature that swam into view, poking up through the dust, appeared to be a huge impact crater. But it stood miles above the Martian lowlands on the peak of an immense mountain, Nix Olympica. And as the dust settled further, the stunning truth emerged that the mountain on Mars was indeed a gigantic volcano. So, geologically, Mars was not a dead planet after all. Vast stretch marks on the planet showed that Mars' surface is shifting and changing on a colossal scale. Mars is beginning to look, geologically at least, more like the Earth and less like the Moon. And then new evidence of water has begun to turn up in surprising ways. Among the many clouds in the Martian atmosphere, some have been found to be composed of water. Then close-ups of the surface have begun to turn up strange, sinuous patterns. Some compare with the patterns cut into the surface of our own planet by the Mississippi River. Slowly, the interpretation emerged that only a fluid flowing continuously over the Martian surface could have caused such patterns of erosion. Some scientists didn't agree, but astronomer Carl Sagan theorized that Mars indeed contained a great deal more water than we'd supposed. The water might remain locked within its crust as permafrost during ice age times such as the present, but during cycles of warmth, when the polar caps release gases to form a heavier atmosphere, the water may be released into clouds. Such clouds could bathe the planet in rains for thousands and perhaps millions of years. If Sagan's interpretation is correct, life could have originated on Mars in favorable cycles and may have adapted itself to harsher conditions as they developed, and indeed may exist on Mars to this day. Exobiologists are studying other environments, even as they prepare to search directly for life beyond the planet Earth. Flying by Jupiter, Pioneer 10 confirmed estimates that within its atmosphere are combinations of gases similar to those in which life originated on Earth. While a second Pioneer is being aimed to curve past Jupiter and fly by Saturn, Earth-based measurements show that a moon of Saturn, nearly the size of the planet Mercury, contains an atmosphere, water, and surprising warmth. A Viking spacecraft is being readied to land on Mars in 1976, carrying an automated chemical laboratory to sample Martian soil for life forms. The discovery of just one bacteria on Mars, or any other body of the solar system, would indicate that the whole chain of evolutions, cosmic, chemical, and biological, is at work everywhere. In that case, the creation of life anywhere in the universe would be more the rule than the exception. In that case, there may be other intelligent civilizations capable of communicating with us. In the impact on ourselves of contact with another intelligent civilization, how it might come about and what the effects might be, is now being discussed by serious thinkers the world over. This symposium at Boston University includes astronomer Carl Sagan, anthropologist Ashley Montague. Krista Stendhal is Dean of the Harvard School of Divinity. Professor Berenson teaches a course entitled Search for Life in the Universe. Professor Philip Morrison of MIT co-authored the first seriously reasoned paper on possible modes of communication with extraterrestrial life. George Wald won the Nobel Prize in 1971 for his work in physiology.
It is now okay to talk about life elsewhere or intelligent life elsewhere, whereas a decade or two ago it wasn't okay. It was considered too speculative to be worth any investment of time.
That the number of stars in our galaxy alone is so staggeringly large, of the order of 10 to the 11 or more. The probability of stars having planetary systems is so high, we think perhaps half. The probability that those planetary systems might be comparable with our own, and that the stars have some kind of an ecosphere, a sphere in which the radiation is suitable for life, that it's not too hot, not too cold, meeting the other criteria, seems so reasonable. These bits of information have come from astronomy primarily, And then we join with the biochemists who tell us about the probable evolution of life here on Earth, the kinds of elements that are necessary for it, DNA molecules and amino acids and the like, amino acids which have now been found in meteorites, that we have now found interstellar molecules floating out in the space between stars, so that you know the materials for a carbon-based life exist. We know that many of the building blocks of life in our own solar system exist off of our planet. If you put these kinds of probabilities together, it begins to lead to the sorts of conclusions that we started with as an initial premise, and which apparently no one on the panel has disagreed, and that is that life must exist in the universe, and it must exist quite abundantly.
The most optimistic estimates, in the view of many, about the number of civilizations that there might be in the galaxy is of the order of 1 million, which means that only one in a few 100,000 stars has such civilizations.
That would mean a billion such places just in our own galaxy that might contain life.
As I believe there's a society of these groups, not just one. There are probably very many. If there's only one, we have no hope of finding them. There are probably thousands, maybe as many as 1 million. They probably already have had a long history of this same experience of finding new ones and bringing them into the network.
And I would imagine if an advanced civilization wanted to talk to us, they would say, oh, well, look, those guys must be extremely backwards. Go into some ancient museum and pull out one of those, what are they called, radio telescopes, and beam it at them.
In 1970, a study of the feasibility for picking up interstellar communication was made in California by a number of radio scientists there, as well as astronomers and others. It's called Project Cyclops. The outcome of that study was that the United States had the technical capability of building a large radio array, which would be able to scan the heavens with fairly great resolution and power sensitivity out to a distance of many hundreds or possibly thousands of light years, with the very distinct possibility of picking up a signal if it were there.
Our present technology is able to detect ourselves anywhere in this galaxy of about 250 billion stars.
First, the people beaming the message will be incredibly alien. Even if their biochemistry resembles the biochemistry Professor Wald teaches, it will not be all that close, you know. It will have enzymes, but it will be, the LD situation will be quite different, and I don't know what chains of enzyme systems they will have at all. And you couldn't eat their food, very likely, even though they're the same biochemistry. Any more than we eat the food of a mushroom. It's very difficult to eat that. So I think, first of all, there'll be two great phases of this eventual time, which I think will come in 10 years or 100 years, or I don't know, maybe longer, when some satisfactory radio telescope work or something similar will acquire evidence of the deliberate beaming of a message, protracted message out into space. So I think that will be easy and, of course, extraordinarily important. You will know very little of what that message says, say that it exists, and maybe some general geographic information from how far away it's coming, from what kind of a star, where. And then I think that you will have pouring into the recorders, week after week, month after month, decade after decade, an enormous body of obviously interesting and meaningful pulses. And you'll be able to read them slowly and fitfully, because they will not be coded, but they'll be anti-coded. That's to say, the people who designed them, the beings who designed them, will have thought very carefully how to make the maximum number of mathematical clues. The best way to single out the meaning will be made available. I think the most important thing that it will bring to us, if we can finally understand it, will be a description, if it exists at all, of how beings disposing of great technology were able to fashion a world in which they could live and persevere and maintain something of worth and beauty for a long period of time.
And finally, it would end our social and cultural isolation. To date, we have been bounded not only into our own countries and into our own small regions on this planet, but most assuredly within our solar system itself. If there are the tens of billions of other civilizations which the predictions indicate might be, then we would join a larger galactic community.
In 1976, we're going to be able to explore Mars for perhaps not so humble microorganisms. Before and after that, we'll be searching the planets and the galaxies for clues to fill in the new patterns we're discovering. The evolution of evolutions that has produced us and the possible millions of other civilizations.
It is conceivable that a spherical ship will land in front of the Washington Monument and a figure with 4 antennas and otherwise looking like the professional football player will walk out and demand to see our leader. But I hope very much that the universe of circumstance is wider than the rather shoddy imaginations of science fiction writers for 30 or 40 years. And I'm pretty convinced it is. We've not found their guidance so great in any but the most modest activities, like going to the moon, which is not very much.
The difference between the spacecrafts of NASA and the lurid flying saucery of that old radio War of the Worlds is the difference between science and science fiction. And yes, between war and peace. It's our own world which has turned out to be the interplanetary visitor. We're the ones who were moving out there, not with death rays, but with cameras. Not to conquer, but simply to learn. We are, in fact, behaving ourselves far better out there than we ever have back here at home on our own planet.